Hello, today I'm going to work through a set of questions that you might typically get in an AS level physics exam on waves. The formulae we will need are N equals C over V, where N is the refractive index of a material, C is the speed of light in air, or more accurately in a vacuum, and V is the speed of light in that material. N1 sine I equals N2 sine R. That means that's Snell's law. When light passes from one medium to another, then the refractive index of the first medium is N1 and the refractive index of the second medium is N2. Sine R refers to the angle of incidence and sine R refers to the angle of refraction. And finally, fringe spacing for a diffraction grating, x, which is the vertical distance on the screen, is equal to capital D, which is the distance from the slit or the grating to the screen, times lambda, which is the wavelength of the light, divided by D, which is the spacing between the slits in the diffraction grating. Question 1. The speed of light in a particular material is 1.24 times 10 to the 8 meters per second. What is the refractive index of that material? Well, here we just need to note that the refractive index of any material is equal to the speed of light in a vacuum divided by the speed of light in that material. We shall always say that the speed of light in a vacuum is 3 times 10 to the 8 meters per second, and we've just been told that the speed of light in this particular material is 1.24 times 10 to the 8th meters per second. And so the refractive index is just 1 divided by the other, which comes out at 2.42. There are no units because it's a speed divided by a speed. So the refractive index of this material is 2.42. Question 2. We're presented with this diagram which shows a ray of light travelling through air and then entering a material which is the same material for question 1. The angle of incidence to the normal as it enters the material is I. The angle of refraction as it goes into the material is angle R. We are told that I is 50 degrees. We're asked to find R. And we're going to use Snell's law for this, which is that N1 sine I equals N2 sine R, where N1 is the refractive index for air, which of course is 1. It's the same as for vacuum, basically. And N2 is the refractive index for the material, which we calculated was 2.42. And we know that I is 50 degrees. So the only thing we don't know is sine R. So sine R is going to equal N1, which is simply 1, times sine I, which is sine 50, divided by N2, which we calculated was 2.42. And if you do that calculation, you'll find that comes to 0.317, which means that the angle R is 18.5 degrees. 18.5 degrees. Question 3. We're presented with two diagrams of fish tanks, which are filled with water. In this particular fish tank, we've got a beam of light which comes from a source within the tank, which is shining up like this and being reflected. No light emerges. In this case, we've got the beam of light shining up like this. It is reflected, but there is also some light which is emerging out of the water. And the question is, why is that happening? Why is there no light coming out of the water in this example, but there is light in this example? And this is all to do with the critical angle. What is happening here is that as the light hits the surface, some of it will be reflected, but some of it will be refracted. But as this angle of incidence increases, so this angle of refraction will also increase until there'll come a point where the angle of refraction is 90 degrees to the normal. And any increase in angle of incidence from that point onwards will mean that no light can be refracted outwards. So this is okay because it's a very narrow angle of incidence. Some light is refracted out. There will come a point where any light that is at that angle will be refracted along the surface. Beyond that point, which is what you've got to here, no light can be refracted out. It is all totally internally reflected. Question 4. Once again, we're given a fish tank. We've got light coming up from within the fish tank, and it is at an angle I such that it is refracted along the surface. So we have reached the critical angle. And that angle of incidence, we're told, is 48.75. And the substance in the tank is water. And the question is, what is the refractive index of water? Once again, we're going to apply Snell's law. N1 sine I is equal to N2 sine R. So N1 is the refractive index of the material that's got the angle of incidence, and N2 is the refractive index of the material that's got the angle of refraction, and the angle of refraction in this case is 90 degrees. So N1 is the refractive index of water. That's what we're trying to find. So we don't know what that is. The sine of I is the sine of 48.75 degrees, is equal to N2, the refractive index of air, which we can regard as 1, times the sine of 90, and the sine of 90 is also 1. So N1 is going to be 1 divided by the sine of 48.75 degrees, and that is 1 divided by 0.752, if you look that up in the sine tables, and that is equal to 1.33. So the refractive index of water is 1.33. Question 5. We are presented with this diagram which purports to represent two waves. Please pardon my drawing, which is not as good as it perhaps could be. And we're asked this question, or these questions. By how much is one wave out of phase with the other, both in terms of radians and degrees? And secondly, what can you tell me about the motion of points A and B? Well, what we can obviously see is that one wave, this wave, is exactly 180 degrees out of phase with this one. So let me explain why. This is one complete wavelength. This length here is one complete wavelength. And this is one complete wavelength from here to here. But if you look, you'll notice that this wave starts, or it should do, when that wave is halfway through. So if you like, this wave is half a wavelength behind, that should be a vertical line. This wave starts when that wave is halfway through. So this wave is half a wavelength behind. So it's half a wavelength behind. But it's also one half of a cycle. This is one complete cycle. This is one complete cycle. So it's also half a cycle. One complete cycle is 360 degrees or 2 pi radians. So if we are half a wavelength or half a cycle behind, then we are 180 degrees out of phase, which is half of 360, or we are, sorry, that's 2 pi radians, that should say, or we are pi radians out of phase. The second part of the question is, what can you tell me about the relative motion of A and B? Well, A and B are going to oscillate up and down, but they are going to be exactly out of phase. They will always be the same distance away from the median position, the mean position, but they will always be out of phase. So if A is above the line, B will be below the line. When B oscillates up, A will be oscillating down. Question 6, we're presented with this diagram which purports to show a standing wave. That is to say, the waves are oscillating, well, these two will be in sync. These two will be going opposite to one another. It's a string, essentially, that is being made to oscillate in one of its harmonics. And the questions are, what is the wavelength of the wave? What can you tell me about the amplitude of any given point on that wave? And how does that standing wave differ from a travelling wave? Well, the first thing we need to see, incidentally, the entire length of the string is 1.5 meters. That one wavelength, one complete cycle is this. And that you can see is 2/3 of the entire length. So since the entire length is 1.5 meters, 2/3 of that will be 1 meter. So the wavelength is 1 meter. Second part of the question, what can you tell me about the amplitude of any given point on the wave? Well, I can tell you that those points on the wave, known as nodes, here and here, do not move at all. They never move. They will always be absolutely stationary. Any other point will oscillate backwards and forwards to the extent that the amplitude allows. So, for example, here, you will get maximum amplitude, whereas very close to the node, the amplitude changes are very small. The final question is, how does this differ from a travelling wave? The point is that on a travelling wave, all the parts of the wave will oscillate between the maximum and, as it were, the minus the maximum level, whereas in a standing wave, each part of the wave oscillates only to the extent that it can do so in order to maintain this shape of wave. Question 7. We are presented with this diagram. This is a radio transmitter. This is a very tall mountain. This is a man with a radio, and we are told that he can receive long wave from this aerial, but not short wave. Why? Well, of course, long wave by definition implies that the waves are very long. In fact, long wave for a radio wave is about a mile. Short wave, of course, very much shorter waves. And what do we know about diffraction? Well, we know that if we have a wave whose size is comparable to the obstruction, a long wave might have a wavelength comparable to the size of the mountain, then it will diffract around the mountain. So in other words, you will get new sources, new Huygens sources they're called, and consequently the information will reach the man and his radio. Whereas if you've got a wavelength that is very, very much smaller, as in the case of short wave, than the mountain, then effectively those waves do not diffract. And there is a kind of a radio shadow caused by the mountain, and consequently you can't pick up the short waves. Question 8, we're presented with this diagram which shows two speakers producing sound, and we are given a, as it were, a point along which a person can walk from A to B to C. At A they hear no sound, at B they hear maximum sound, the intensity of the sound is measured by this diagram here, and at point C there's no sound. So remember, they're walking from A to C. At A there's no sound, at B there's a maximum sound, and at C there's no sound at all. And what we're asked to identify is what is the distance from A to C if the separation of the speakers is 2 meters, the distance between the speakers and, as it were, the screen or the line on which the man is walking is 8 meters, the speed of sound is 330 meters per second, and the frequency of the sound we're using is 1320 hertz. And we're also asked to identify what is the wavelength of the sound. Well, we can use a general formula that the speed of a wave is equal to its wavelength times its frequency, which means that lambda is going to be c divided by f, and we've been given those two pieces of information. C is 330 meters per second, frequency is 1320, so the 2 divided gives you 0.25 meters. So the wavelength of the sound is 0.25 meters. Now we need to know what the separation of the minima is, the distance A to C, which is essentially the width of one fringe. And for that we're going to use the formula x equals lambda d over d, where x is indeed the distance A to C, that is the separation of two consecutive fringes, in this case 2 consecutive dark fringes if they were light, but in fact it's sound, so it's 2 consecutive silent fringes, is equal to the wavelength times d, which is the distance between the source and the screen or the observer, divided by little d, which is the separation of the 2 sound sources. So therefore we get that lambda, which is 0.25, we just calculated that, times d, which is 8 meters, we are given that, divided by little d, which is 2 meters, and that gives you 1 meter. So the separation of the 2 silent zones, A and C, is 1 meter. Question 9. We're presented with this diagram. This is a diffraction grating with 4 times 10 to the 5 lines per meter. The diffraction grating produces fringes. The first will be the 0th fringe. This is the first fringe. This is the second fringe. We're told that the light that is used, which will actually be yellow light, has a wavelength of 6 times 10 to the minus 7 meters. And we are asked 3 things. What is the angle from the horizontal to the first fringe? What is the angle to the horizontal of the second fringe? And will there be a 5th fringe? Well, here we're going to use the formula which I didn't give at the beginning, or at least I didn't give it in this form. D sine theta equals n lambda, where d is the spacing between 2 consecutive slits, sine theta is the angle theta that we're trying to find, n is the order of the fringe, first, second, so 1 and 2, and lambda is the wavelength of the light. What we're trying to find is the sine thetas of the 2 respective angles. So what is d? Well, if there are 4 times 10 to the 5 lines per meter, then the separation between any 2 lines is 1 over 4 times 10 to the minus 5 meters. So consequently we can now say that sine theta, and let's do this for the first fringe, so we call this sine theta 1, is equal to n lambda divided by d, and that's going to be 1 times lambda, which is 6 times 10 to the minus 7, divided by d. Well, d is 1 over 4 times 10 to the minus 5, so in other words the 4 times 10 to the minus 5 comes up here. Oops, sorry, just spotted an error. You probably already have. If there are 4 times 10 to the 5 lines per meter, then d is 1 over 4 times 10 to the plus 5. And similarly, you'd have to have a plus 5 here. Right, so let's multiply that out. You've got 6 times 4, that's 24. 10 to the minus 7 times 10 to the plus 5 is 10 to the minus 2. That's sine theta 1, which means that theta 1 is equal to 13.9 degrees. We do exactly the same calculation, but instead of having n, this is for sine theta 2, n now is going to be 2, so it's going to be 2 times 6 times 10 to the minus 7 times 4 times 10 to the 5. And that's going to be, of course, just twice what we got before. We're now going to get 48 times 10 to the minus 2. That's sine theta 2, which means that theta 2 is going to be 28.7 degrees. So we've measured the angles, or we've calculated the angles for the first order and for the second order. The third question, or third part of the question we had was, is there a 5th fringe, a 5th order fringe? In other words, does n equal 5? Well, let's work it out. We're going to use the formula d sine theta is equal to n lambda. And let's say, therefore, what would sine theta be if there were a 5th order? It would be 5 times 6 times 10 to the minus 7 times 4 times 10 to the 5th, using exactly the same formula as we had up there. That will give us 5 times 6 times 4 5 6s are 30, times 4 is 120, times 10 to the minus 2, which of course is 1.2. Sine theta cannot be 1.2 because the maximum value of sine anything is 1. Sine 90 is 1. You can't get more than that. So consequently, you cannot have n equals 5. Question 10. We're given a diffraction grating with 3.7 times 10 to the 5th lines per metre, and that produces, light is coming through it, it produces the first fringe, the first order fringe, at an angle theta, which we're told is 14.2 degrees. And we're asked to find the wavelength of the light. Once again, we're going to use the formula that d sine theta is equal to n lambda. D, remember, is the separation between two consecutive slits. D is going to be, therefore, 1 over this term here, and I'll get it right this time, 1 over 3.7 times 10 to the 5th. That's D. So consequently, since now what we want to know is lambda, this term here, lambda is going to be d sine theta divided by n. N, of course, is 1 because we're looking at the first order fringe. So that's simply going to be equal to d, which is 1 over 3.7 times 10 to the 5th, times the sine of 14.2 degrees. And if you calculate all that out, you will find that lambda is equal to 6.63 times 10 to the minus 7 metres. Question 11. We're presented with a diagram which purports to show a fibre optic cable. A light ray comes in from the air into this fibre optic, which is made of glass. It then is totally internally reflected from the wall, and the angle of total internal reflection is 80 degrees. And we are asked to find the angle of incidence. Well, we can see from the fact that this is a right angle triangle here, that if this angle here is 80, then this angle here is, which is the angle of refraction, is 10 degrees. And so we can simply say that we're using the formula n1 sine I equals n2 sine R, where this is air, and therefore n1 is n1 for air. This is glass, so n2 is n2 for glass. So we've got n1, which will be 1, times the sine of I, which we're trying to find, is equal to n2. Well, the refractive index for glass we're given is 1.5, times sine R, and we said that the angle of refraction is 10 degrees. And if you work that out, you will find that I is equal to 15.1 degrees. Question 12. We're given a diagram which shows a standing wave, which means that it oscillates like this. And we're told that the speed or the velocity of the progress of this wave is 6.2 meters per second. Of course, it's not a travelling wave, but nonetheless there is a motion which it purports to be velocity along this wave, and that's 6.2 meters per second. And we're asked to know what is the vibration frequency, since somebody's actually wiggling this piece of string in order to get that shape of a wave. Well, we know that the wavelength is 1.2 meters because the entire length of the string is 1.2 meters, and this is one complete wavelength. So lambda is 1.2. We know that the velocity is 6.2, and we know that the velocity of a wave is equal to its frequency times its wavelength. That means that its frequency is its velocity divided by its wavelength, which is 6.2 divided by 1.2. And that comes to 5.2 hertz. So the person who is wiggling the rope up and down is wiggling it up and down 5.2 times per second in order to create that wave. Question 13, we're asked to find the critical angle when light goes from glass into water. That is to say, what is the angle of incidence that will cause the light to refract along the surface such that the angle of refraction is 90 degrees. And the second part of the question is, what is the critical angle when light goes from water to glass? So let's do glass to water first. Once again, we're going to use the formula N1 sine I equals N2 sine R. N1 is the refractive index in glass, and we're told that that's 1.5 and water is 1.33. So now we've got that the refractive index in glass is 1.5 times the sine of the angle we're trying to find is equal to 1.33 times the sine of R. Well, the sine of 90 is 1, which means that the sine of I is 1.33 divided by 1.5, and that's 0.8866. And when you look that up, or you use your computer to tell you, you'll find the angle of incidence is 62.45 degrees. So when the angle of incidence is 62.45 degrees or greater, then you will get no refraction. All the light will be reflected, or at least at that precise angle, the light will be refracted along the surface. If that angle goes up even by a slight amount, all the light will be reflected. Now comes the question, which is the trick question. What is the critical angle when light goes from water to glass? Well, then you've got N1 sine I equals N2 sine R. This time it's the other way round. We've got water going to glass, so the refractive index of water is 1.33 times the sine of incidence, which is the critical angle, equals N2, this time it's 1.5 for glass, times the sine of 90, which is 1. So we've got the sine of I is 1.5 over 1.33. And we needn't go no further because that is greater than 1. 1.5 divided by 1.33 is greater than 1. And you can't have a sine I greater than 1. So there is no critical angle when you go from water into glass. And the final question, question 14, what is the speed of light in glass if its refractive index is 1.5? And here I'm just going to use the formula that the refractive index, the definition of the refractive index is the speed of light in vacuum divided by the speed of light in the material, which means that if we rearrange that, we find that the speed of light in the material, which is what we want, is equal to c divided by n. That's 3 times 10 to the 8th meters per second is the speed of light in vacuum or air, divided by n is 1.5, and that gives you 2 times 10 to the 8th meters per second. So in glass, the speed of light is 2 times 10 to the 8th meters per second.